In this video, I'm going to go over some of the calculations that we can do using the central limit theorem. And what we'll see is that these calculations look almost identical to the calculations that we've previously done with the normal distribution. The only difference is the formula for the z-score. So keep that in the back of your mind as I go through this. What we're doing is basically the same as what we've done with a really important difference. The z-score is calculated in a different way. So don't treat this as a totally new thing. Treat this as a modification on what we've done before. In this problem, we're told that a manufacturing company produces ball bearings whose diameters are normally distributed with a mean of 5 millimeters and a standard deviation of 0.2 millimeters. And we're going to then go and answer some questions about sampling distributions. Importantly, because we're told that the original variable is normally distributed, it doesn't matter what the sample size is. We can do these calculations no matter how small the sample size is. The central limit theorem tells us this because the original variable is normally distributed. If the original variable weren't normally distributed, we would need to have a sample size of at least 100 for the central limit theorem to apply. And I'll point out that number 100 is really just a decision we've made in this course for how approximate we're willing to have our results be. If the original variable is normally distributed, then the sampling distribution is exactly normal. If the original variable isn't, then as sample sizes get bigger, the sampling distribution is closer and closer to normal. In our course, we've decided 100 is our boundary for this is close enough to normal, and we'll be willing to use the central limit theorem on these calculations. All right, so let's dive right into problem one. A manufacturing company, we said, is producing these ball bearings, and we want to know the probability that a randomly selected sample of 24 ball bearings will have a mean diameter greater than 5.1 millimeters. In other words, we want to know what proportion of sample means of samples of size 24 will have an average diameter, a mean diameter greater than 5.1. So our picture looks like this. Now here, notice I'm drawing actually the sampling distribution, not the original distribution. These numbers are sample means. And the average sample mean will have a value of 5. And we're asking about number 5.1. I don't worry about exactly where I put it as long as it's on the correct side of the mean. And I want to know the probability that we get a value greater than this. I always draw my picture first because if I don't draw it first, I might forget to draw it. I might go on autopilot and I might make a mistake and get a wrong answer. By drawing it first, it's much more likely that I won't make a mistake. Already in the back of my head, I'm thinking, this is not just p norm. This is 1 minus p norm because it's area to the right. And so hopefully that'll avoid a potential future mistake. So to calculate z, and again, this is the big distinction, well, instead of x, I write x bar because we're not talking about individual diameters. We're talking about average diameters. That's not that important of a distinction. I don't tend to see people making errors because of that. The important difference is that this z-score, I don't have just sigma in the denominator. I have sigma over the square root of n. Because the sampling distribution does not have the same spread, it does not have the same standard deviation as the original distribution. It's narrower. Its standard deviation is sigma over the square root of n. So let's fill in everything we know. The value I'm wondering about is 5.1. The mean is 5. There's the average sample mean is accurate, it's 5. The standard deviation of the original values is 0.2, and n is 24. And so I've got to figure out what this z value is. I'm going to type this into RStudio. Now notice I always put parentheses around my numerator because I want to divide that whole thing by the denominator. But importantly, I also want to divide by the whole denominator. And the whole denominator is 0.2 over the square root of 24. And so notice I put that number, 0.2 over the square root of 24, itself in parentheses. I want to divide by the whole thing. I don't know what just happened here. Let's just type some random thing and see what happens. Okay, so I don't really know what just happened there. That was a weird number, but let's let's try that thing again here. So I'm just going to retype because I must have typed something that was not what I wanted to type. I don't think that had anything to do with what I typed. I think that had to do with some issue. So sometimes when you get these red error messages, right, they're best to ignore and just say, look, I'm just going to try that again. All right, there we go. That's a more reasonable answer, right? 2.45. So that's my z value. Now, I want to know the area to the right, the proportion above 5.1, or the probability that a randomly selected sample is above 5.1. And so I have to do 1 minus p norm. P norm tells me area to the left. I want area to the right. And so let's type that in, and let's hope that the weird errors have ended. They have, at least for now. 0.0071. So this is my answer. This is the probability that a randomly selected sample would have a sample mean greater than 5.1. A few observations. One, I could ask the same question in a few different ways. Instead, as I said before, instead of a randomly selected sample, I could have said what proportion of samples are greater than 5.1 in terms of sample mean. I also could have said what percentage are greater than 5.1 in terms of sample mean. That would be the same exact process. If the answer was supposed to be a percentage, I would move the decimal place. The second thing is that I could ask very similar questions in the same vein as the other normal distribution calculations. I could ask, the probability of a sample mean less than some number. And so then I would just use p norm, right? I could ask the probability that the sample mean falls between two numbers. Then I would do p norm of the bigger minus p norm of the smaller. In any case, the only difference between what I'm doing here and what we did with just standard normal distribution calculations is this formula for z. So I've talked about the first type of question, where we're given a value and asked for a percentage or proportion or probability. I want to do the opposite type of question, where I'm given a percentage or proportion or probability and asked for a value. So here, what is the 90th percentile of the sampling distribution of sample mean diameters for samples of 24 ball bearings? A tough question to even say. What is this asking us? It's saying, look, here's our sampling distribution. Average sample mean, middle, because it's symmetric here also, is 5 millimeters. What number, what sample mean x bar, is greater than 90% in terms of its value of all other sample mean? So I want to know the sample mean x bar such that the area to its left is 0.9. Again, this is going to look exactly like what we did with normal distributions, except that my formula for z is going to be different. And so if you recall with normal distributions, what we start by doing is figuring out what z-score corresponds to this value. Right? So 5, the mean, corresponds to a z-score of 0. What z-score corresponds to this x bar? Well, that's just q norm of 0.9. Q norm tells us the value on the standard normal distribution that has an area of whatever you type in to its left. And so I get 1.28. Now I set up the formula for z. And I plug in everything that I know. I know what z is. I don't know what x bar is. That's the thing I'm trying to find. I know what mu is. I know what sigma is. And I know what n is. There's two approaches at this point. One approach, which is not what I'm going to do, but is fine as long as you are careful with rounding, would be just to calculate what this denominator is. To say, I don't really want to deal with this. This looks complicated. Figure out what the denominator is and plug that in to your formula and then solve that. If you're going to take this approach, just remember, unless you really want to think about what rounding error is going to do when you start multiplying by things, don't round, right? I mean, I guess let's be fair. Our studio has already rounded this, but leave a bunch of decimal places. Work with, what do we have here? I guess 8 decimal places. Keep them all there. other option, which is what I'm going to do, is just to not simplify until the end. So what I'm going to do is I'm going to multiply both sides by the denominator. And so that gives me, I multiply both sides by 0.2 over the square root of 24. That gives me this equation. And then if I move 5 over, so I add 5 to both sides, and now I can just type all this into RStudio without ever having rounded. And I'll point one thing out. You might notice correctly that I have rounded, right? 1.28 was rounded. I could do 0 rounding. I mean, the program might be doing some internal rounding by, instead of 1.28, just typing Q norm of 0.9. I could type it all into one thing, but I'm not going to do that. So I'll do 5 plus 1.28. Remember, I have to put in a times sign. Now this thing should be in parentheses. And I'll click enter, and I get 5.05. So the 90th percentile of these sample means is 5.05. 90% of sample means of samples of size 24, where we're taking the average diameter, 90% of them are less than 5.05. Again, I could do all sorts of, not really all sorts of, there's two main other types of calculations. I could, instead of having an area to the left, the 90th percentile, I could ask, what sample mean do 20% of sample means fall above, or something like that. And again, I would do the exact same thing that I did with a normal distribution calculation that wasn't sample means. So I'd have to change this number. And I could also ask about, the middle 95% of sample means, or something like that. And if you're wondering how to do that, go back to that normal distribution video and just substitute in this formula for Z. That's really the only difference. So hopefully that was helpful and gets you started on some of these sampling distribution calculations. They're really not too bad if you view them as the normal distribution calculations, which you're hopefully getting familiar with, plus this added detail that we have a different formula for Z.